everyone, now it's me again. We are on our lecture note 3 of 3, still under chapter 1, topic number system, subtopic complex number. Okay, so complex number is quite new to you, right? Complex number is a combination, it's a combination of real number and imaginary number that can be expressed in the form of x plus yi, where x is the real number and y is the imaginary. Okay, x is real and y is the imaginary. I here denoted that y is the imaginary part. And I is known as the imaginary number that satisfies the equation I equal to set negative I. So this is the definition of the I. I is equal to set of negative 1, or I square. When you square both sides, it will become I square equal to negative 1. And complex number can be written as z equal to x plus yi, known as Cartesian form, where x is the real part and y is the imaginary part of the complex number. So by definition, I equal to a set of negative 1. So when we square both sides, it will become I square equal to negative 1, and it continues for I cube. You can see the process here. Try to understand the process that goes on here. Try to do it by yourself. Okay. The important thing is you know the definition. This is the definition. So everything down below here starting from this very important definition. Okay. So we try to look at example 12. Where is the example 12? This is the example 12. Now, the first thing is we need to simplify this because we noticed that from our previous lesson, from your what you have go through during your Form 4, Form 5, square root cannot be negative. Okay? Right? But it is important for us to know that before this, we are going through this definition whereby I is equal to set of negative 1. Right? From our definition, from the previous page, I is equal to set of negative 1. So, we need to rewrite this in the form of negative 4 is equal to negative 1 multiplied by 4. Right? And by the law of sets, we can separate it or break this up into become a separate set, negative 1 multiplied by set of 4. Can we solve this? Okay, again, by definition, this is that we get from our previous page, which is set of negative 1 is equal to I. So this one, we can write it as I. What about set of 4? Set of 4 is equal to 2. So, this one is equal to 2. Our final answer is 2I. Right? So whatever it is goes to our definition. Okay, what's our definition again? I is equal to set of negative 1. That's a very simple example, right? Now we go to more complex one. Okay, we go to example D. Can we go to example D, class? Right, go to your example D, whereby we have -2 minus set of -48 divided by 2. So again, here, okay, negative of set, negative 48, set of negative 48, we can break up to, it's actually set of negative 16 multiplied by 3, right? Okay, so from here we can break this into set of -1 multiplied by 16 multiplied by 3. Is it? Okay, now we go to our equation. So this one, it will be -2 minus, okay, I want to put -1 at the back. So this one becomes 16 multiplied by 3 multiplied by -1, because we know from our definition, set of -1 is equal to set of -1 equal to, yes. So this one, it will become -2 minus set of, by law of set, you can break this up, right, into 1 by 1. Set 16 multiply by set of 3 multiply by set of -1. Okay, so I think you can set of -16 multiply by set of 3 multiply by set of -1 divided by 2. And this one will become, I don't have enough space here, but it's okay, as long as you can understand what I mean, so that's no problem. We have here 4 set 3i over 2. Okay, is that the final answer? Not yet, because final answer means very final. You cannot do anything anymore. So now, as we can see, we can, okay, this one become 1, this one become 2. So our final answer is -1 minus 2 set 3i. Okay, so that is final answer. We cannot do anything anymore. We cannot simplify it anymore. Okay, now we go to operations that involving complex number. Before this, we go through definition, right? So we are done with the definition. We go to the complex number operation. Okay, to add or subtract the complex number, we simply add the real part separately and the imaginary part separately to get a new complex number. So as we can see here, we have two complex number here, but at the end of it, we will add the real part separately from the imaginary part. Okay, and we get a new complex number there. Right? We add A together with C because this A and C, A here is real part. Okay, so that's why A plus C. And B here is the imaginary part. That's why B plus D. Okay, and the same thing we do with the subtraction. We minus the real part separately from the imaginary part. This is the imaginary. Okay, so it's very simple for addition and subtraction. Right, so that's for addition. For addition and subtraction, we separately add or subtract the real part and the imaginary part. So we get a new complex number. Now we go to multiplication of complex number. Okay, for multiplication of complex number, what can you see here? Okay, actually the general idea is you can multiply complex number just like you multiply a traditional binomial. Okay, so just like this. So as you can see here, it's actually like we multiply our traditional binomial to binomial. So this one, okay, like this. So at the end you will get this. How to get this? We get AC plus ADI plus CBI plus BDI square, and I square is equal to -1, right? So AC minus BD plus CB plus AD here, I. Okay. So why it become like this? Because I square here will become -1. That's why after this, we can notice that I square here will eliminate and it changed to -1. That's why AC minus BD, we get this. Okay. Now we go to example. Straight away go to the example. We try to solve example 13 first, focusing on both A and B. So for this one, what should we do? We simply just do a normal operation here. This one become 12 minus 9i minus 10 plus 25i. So this one involving addition and subtraction of complex number. We will add or subtract the real part separately with the imaginary part. So it will become 12 minus 10. Okay, 12 minus 10. This one we have plus -9 plus 25i. So here it will become 2 plus 16i. So this is the final answer. Okay, very simple. And now we go to the multiplication of two complex number. Okay, so just like a normal multiplication, set 3, we just expand the bracket, right? Then the general idea is just like we expand the bracket. We have -I, set 3, set 5, plus I, set 5, set 3, minus I square, set 5 square. So at the end we get 3. Okay, this one will eliminate, right? Because negative here plus, then we don't have it anymore. And this one I square equal to -1, so negative multiplied by negative, we get a positive. So plus by 5. So at the end we get 8. We must be very careful. Okay, when do maths, you need to be very, very careful. Okay, that's it for example 13. And then we go to now equality of two complex numbers. Alright. So now we need to, example 14, determine the values of x and y. Okay, just compare left together with the right. So when you have symbol of equal here, meaning left is equal to right, so we just compare. So to compare this, we need to solve this and make sure we get a correct answer. 5 multiplied by 3, we get 15 plus 5i minus 3i minus I squared. Okay, so from here, by definition, I squared is equal to negative 1. So, 15 plus 5 minus 3 equal to 2i minus negative 1 here. So, here we get 15 plus 2i plus 1. And final answer is 16 plus 2i. So, at the end, by comparing, get x is equal to 16 and y equal to 2. Right? Okay, and that's it. Okay. Now we go to conjugate of a complex number. For previous example, you can try to do it by yourself. Okay, we cannot solve everything in this video. We go to a conjugate of a complex number. Okay, so two complex number which have equal real parts. Okay, they need to have equal real parts but opposite sign of imaginary parts are called complex number. They have what? Opposite sign of what? Imaginary parts. Wow, to highlight that. So means it's very important. Please notice this. Opposite sign in the imaginary parts are called complex conjugate. Okay, where when we have z equal to a plus bi, then its conjugate written as z. This the symbol in up of the z, I mean in the one here, okay, up here, referring to the complex conjugate, is equal to a minus bi. Okay, they are different in the imaginary part. Okay, the symbol is completely different, opposite to each other. So for example, we can try to solve A. Example 16a. Okay, here. How to solve this? We need to, for a fraction, we don't want the denominator in the form of I. So what should we do for that? Okay, how to eliminate the I? We need to multiply by the conjugate. Okay, what's the conjugate for 3i? Negative 3i. So that's what should we do? Okay, so we multiply the numerator and the denominator by its complex conjugate, which is multiply by negative 3i. So, negative 3i. Now, our fraction will become 2 minus 3i multiplied by negative 3i over 3i multiplied by negative 3i. Okay, so now we can clearly see that now it becomes negative 6i plus 9i squared over negative 9i squared. Okay, what happened to the I squared? So by definition, From our previous page, we get that I square equal to negative 1. So, negative 6i plus 9, negative 1 here. Down below here also negative 1. So now we get negative 6i minus 9 over 9. So is that the final answer? Not yet, because we can still simplify this. How to simplify this? So this one will become 3. This one will become 3. This one will become 2, right? So at the end, it will become negative 3 minus 2i over 3. Final answer is negative 1 minus 2i. Okay, because normally we put the real part in front and the imaginary part come after it. Okay, that's why, just to make it look normal. If not, it's look abnormal. So we want to make it look normal. Okay, this is the answer. Negative 1 minus, 2 over 3 here. Okay, 2 over 3. Negative 1 minus 2 over 3i. Okay, so go through step by step slowly. Don't have to rush. If not, you will make a mistake. Make sure you don't make any mistake. Okay, that's for example 16a. Let's go to example 16c. Okay, like our a, so what should we do to solve this fraction? We need to multiply by the conjugate. Conjugate of what? Numerator or denominator? Absolutely the denominator. Okay, please don't get confused. Conjugate of the denominator. Okay, any fractions also we solve fraction with the complex conjugate of the denominator. Meaning we don't do anything with the numerator. Okay, they just follow. So here we need to multiply by, what's the complex conjugate of the denominator? Negative 2 plus 5i, because the imaginary part is completely opposite from the one that's not conjugate we want to conjugate with. So negative 2 plus 5i here. Now we can solve it. How to solve? So this one, it will become 11 minus 2i negative 2 plus 5i over negative 2 minus 5i multiplied by negative 2 plus 5i. Okay, so for a conjugate, we still use this formula whereby a minus b multiplied by a plus b equal to a square minus b square. Okay, so for this one, you want to do a more difficult operation. So this one here, down below here, for the denominator, it will become, by using this formula, so a is negative 2, right? Negative 2, oops. So our negative 2 will be square minus our b is, what is our b? Our b is 5i squared. Our b is 5i. Our a is negative 2. Our b is 5i. Okay. So, okay, the operation up here is, okay, here, negative 22 plus 55i plus 4i minus 10i squared. Are you following me? Okay, I hope you are. So now, just solve everything, do it properly. So negative 22 plus 55i plus 4i. So this one I square, it will become negative 1. So negative 1 multiply by negative become positive. So here we plus 10. Okay, over this one will become 4 minus 25 I square will become negative 1. Negative multiply by negative become positive, right? So this one plus 25. Is it? So now it will become negative 22 plus 10 become negative 12 plus 59i over 29. So our final answer, either you want to put it in that. So better we put this in this version to make it look more normal. Plus 59 over 29i. So that's our final answer. So that's all, class, for today's lesson. For this video, thank you for your cooperation and attention. Hi everyone. So from this video, we are going to learn how to determine a complex number in polar form. Okay, we know that before this, we already know about this original form of complex number. Now we want to change it into polar form. So to change it into polar form, we need to know what is modulus of z and what is the argument of z. So let's us try to familiarize ourselves with Argonne diagram. Okay, because to find modulus of z, to find the argument of z, we need to understand how to draw Argonne diagram. Alright, to draw an Argonne diagram, we need to draw an axis first, of course. Okay, we have our real axis and imaginary axis. Okay, real axis is for the real part of complex number, and imaginary for the imaginary part of complex number. And we have our origin here. Let's say for this example, z equal to a plus bi. Our real part is a. Okay, a is somewhere here, and our imaginary part is b. So b somewhere here. So the point P, AB is somewhere here. And then we have our theta. Okay. So this is A and this is B. Alright. So from this diagram, it's written here that our OP, how to find the length of OP, set of A square plus B square. So what's the use of the length? Okay, length of OP is called modulus of Z. It denoted by modulus of Z, always positive. Therefore, modulus of Z is equal to set of A square plus B square. Or we can call it as equal to R. Our R is equal to modulus of Z equal to set of A square plus B square. And then we have our argument of Z, which is equal to theta. Which theta? This theta. Okay, this is the theta that we are talking about. Okay, this theta, which is it is measured in radians, and it is angle made by the line OP with the positive x-axis. Alright, angle that measured in radians, that is theta. So how to find theta? Satisfying this equation, tangent theta equal to b over a, and must be in this range from negative pi until pi, denoted by argument of z. Alright, so you can read by yourself the statement here. Now, how to find the angle? Okay, to find the angle, first and foremost, we must know where is our position of complex number. Is it in the first quadrant, second quadrant, third quadrant, or fourth quadrant? Alright, we are focusing on first and second quadrant first. For first quadrant, to find the theta is very easy, which is, of course, tangent theta equal to modulus of b over a. So theta equal to tangent inverse modulus of b over a. It's direct, right? Directly, I mean, we can see it obviously. That's the way. What about if it is in the second quadrant? So if it is in the second quadrant, we can see that our complete, half circle here is from 0 until from 0 until pi, right? Our half complete circle is pi. So we want our theta. Okay, this is the theta that we want. This is the theta that we want. Which one is the angle that we don't want? This is the angle that we don't want. Okay, this is the angle that we don't want this angle. So that's why you can see here that the way to find our theta is equal to pi minus tangent inverse of modulus b over a. Okay, we minus this area. And that we get the value of theta that we want. Okay, if it is in the second quadrant, we must use pi minus tangent inverse of modulus b over a. Alright, what about if our complex number is in the third and in the fourth quadrant? Okay, you can see from this formula here, the way to find it, let's say our complex number in the fourth quadrant. Then the way to find the angle is just like the way we find angle for first quadrant. But different is we put our minus sign in front of the angle. Okay, same goes with if our complex number in third quadrant. The way to find the angle is just like our way of finding the angle. If our complex number in second quadrant, it just that we put minus in front of the angle. Right? We put minus in front of the angle. Okay. So that's it, how to find the angle. And now we go to example. Not yet the example. So we already find our z, our modulus of z, and our argument of z. What is our polar form? So what's the use of it? Polar form is another way to represent a complex number. Okay, so let's say our original complex number is in this form, z equal to a plus bi. So we need to change it into r cos theta plus I sin theta, where our r equal to modulus of z and our theta equal to argument of z. And then our new polar form is z equal to r cos theta plus I sin theta. So to form a complex number, we need to find our modulus of z and our argument of z. So it is very important for you to know how to find it. Okay, now we can go to our example 17. Alright, so example 17a first. Okay, so from our z equal to 4 plus 3i, what is our a? So from here, our a is equal to 4 and our b is equal to 3. If we have a and b, we directly can find our modulus of z, which is equal to r as well. So our modulus of z, which is equal to r, equal to 4 square plus 3 square set of 8. So the answer is equal to 5. Okay, we have our r, or our modulus of z. So now we need to find our theta, or our argument of z. So to find our theta, we need to draw an Argonne diagram, because we want to know where is our position of complex angle. complex number, sorry. So this is our real part and this is our imaginary part. So we have our positive A and positive B, right? That means our complex number is in the first quadrant, somewhere here. This is our position of Z. Okay, so Z there. This is our theta that we want to find. If it is in the first quadrant, it's very straightforward, which is theta is equal to tangent inverse of modulus B over A, 3/4. And the answer must be in radian. So from your calculator, you can know that the answer for this is 0.6435 rads. Alright, so when we have our R and we have our theta, what's the purpose of finding R and theta? To convert it into polar form. So our polar form will become Z equal to R cos theta plus I sin theta. And that's the answer for our example 17a. It's very simple, alright? We want to find our A and B first. So from there, we find our modulus of Z, or also known as R. And then we draw an Argonne diagram. From Argonne diagram, we know the position of our complex number. That's very important so that we get the right value of our theta. And then final one is we just insert everything that we have into polar form. Okay, that's the way. So now let's go to our C, example 17C. So what should we do? We find out first what is our A, negative of 3, and then what is our B, negative of 1. From A and B, we can directly find out what is our modulus of Z, which is negative 3 square plus negative 1 square Z. And then calculate by using your calculator, you get value 2. After that, we want to find our theta, but we must draw an Argonne diagram first so that we know the exact position of our complex number. Okay? So now both our real part and imaginary part is negative. So where is the position? So it should be in the third quadrant. Somewhere here is our Z. Okay, so if it is in the third quadrant, then we know that we must put negative in front of it. Okay, and the way to find it, just like the way we find the angle if it is in the second quadrant, which is, we must put pi minus. Minus by what? Minus of tangent inverse modulus B over A. So our B is negative 1 over negative 3. So modulus here meaning that if we get negative inside, but we must make it positive. So from our calculator, the value that we should get is negative 2.618 radian. Okay, now we have our R, we have our theta. That's not final answer yet. We must put everything in polar form. So Z equal to R. Our R is 2. R cos theta. So our theta is negative 2.618 plus I sin theta. So that's the answer. Very easy. Okay? Very, very easy. Now we go to a more complex one, but it's not that complex. we go to example 18, our final example for this topic finally. So we have our z equal to 2 minus I. Determine z plus 1 over z bar in the polar form. So we know that polar form, we must know what is the r, which is what is modulus of z, and we need to find the theta as well. Now, what is our z bar here? Z bar here meaning the conjugate of z. What is conjugate of z? Okay, meaning they have similar real part but opposite sign of the imaginary part. So this one 2 plus I because opposite sign of the imaginary part. Now our z plus 1 over z bar is equal to 2 minus I plus 1 over 2 plus I. Okay, now what should we do? If we have fraction, we need to rationalize the denominator. So how to rationalize a complex number? We need to multiply by the conjugate because we don't want a complex number in the denominator. Or the same thing we need to do if our set is in the denominator. So multiply with the conjugate. The conjugate is 2 minus I. Okay. So now we have this. What should we do? So now it becomes 2 minus I plus 2 minus I over. So what? So I just want to remind you, if the conjugate meaning we multiply A minus B multiplied by A plus B, it becomes A square minus B square. So that will happen here, which is 4 minus I squared. That's why we get this. Okay. So now simplify it. 2 minus I over 5. Okay, that's not end of it yet. We need to continue until we get a better complex number. So now, okay, I hope you understand what I'm doing here. So 10 minus 5I plus 2 minus I over 5. And then it will become 12 minus 6I over 5. Okay, to make it easy to find our A and B, we separate our real part and imaginary part. So our real is 12 over 5 minus 6 over 5I. Okay, so from this complex number, our new complex number that we already simplify, we can get what is our A and our B, which is our A is equal to 12 over 5 and our B is equal to negative 6 over 5. We have our A, we have our B. We can get our modulus of Z and our theta. So from A and B there, we can find out that our modulus of Z is equal to 12 over 5 square plus negative 6 over 5 square third. So we get the value of 6 5 over 2. And then we need to find the theta, which is argument of Z. But before that, we need to know where is the position of our complex number. So, if our A is positive and our B is negative, obviously it is the position is in the fourth quadrant. So this is our real axis and imaginary axis. Our complex number is somewhere here. And this is the theta that we want to find. Our theta is, how to find the theta? How to find the theta? 12 over 5 minus 6 over 5I here. So, theta is actually, because it is in the fourth quadrant, so we know that in front of the tangent inverse must be negative. In front of tangent inverse of what? B over A, modulus of negative 6 over 5 over 12 over 5. So by using calculator, we get the value here is equal to negative 0.4636 radian. So because we already have our R and our theta, so we can put everything in order of polar form. So our new polar form is equal to Z equal to sec 5 over 2 cos negative 0.4636 plus I sine negative 0.4636. Okay, that's it. So it's very simple actually, don't worry. Okay, that's all.